The very last lesson in Math AS that you've studied regarded binomial expansion. If you'll remember, this was basically what we covered. So you learned that every time you have a binomial in this form, it is possible to expand this binomial expression by using this this rule that you can also find in MF19. Let me get there. You could see it over here. Okay, this is again a simplified version of what you have here. And I'm going to start by going over very quickly the stuff that you've learned on Pure Math 1. So what happens over here? Whatever your A and your B is, as you expand, the power of your A starts with whatever your N is, the power of B starts with 0, and these are combinations N, 0, N being whatever power you have there. And as you go to the left, the combinations are calculated like the way that you have here. By now, I'm assuming that you know what I'm talking about. You just have to plug this in your calculator, and this will yield a number, a coefficient. And then the power of A goes down by 1 for every new term, and the power of B will go up by 1, starting in 0 for every new term, until you end up with the last term, which is combinations N, which is always 1. Your A is going to be powered to 0, so this is also going to be 1. And finally, whatever your B is going to be powered to N. Again, in MF19, this is just shown as B to the power of N, as you can see there. For the same reason, the first term is just A to the power of N. What were the circumstances in which this could be used? This could be used every time N was a natural number, and yes, that's it. N would be a natural number, and the series is finite. That is, it ends at a particular place. This topic, this chapter, is going to explore this and will allow you to expand binomials in other situations, particularly when you have fractions. Okay, so let's see what happens when you expand this. When you expand this, the expression is going to be pretty much the same, but now there is a very important difference. The difference is that your N can be any real number, doesn't have to be a natural number. Okay, so it can be a fraction, can be a negative number, etc. And what will this do? This will expand the binomial, introducing new terms that can go to whatever number of terms that is predefined or the question asks. And the higher the number of terms that you add, the closer the value will be to the one that is represented by the expansion. One note here that I forgot to mention. Last year, you also learned that every time A is 1, this expression can be simplified into this. Okay? And again, what are these things over here? These are the calculations that you have to perform if you want to calculate yourself without the use of the calculator, the value of the coefficients that you have over here. Okay? If you try to adapt this formula for the circumstances in which A is 1, you'll end up with this. Okay? And if you look to the new expression that you are going to use this year, this is pretty much the same. But there is one difference. It doesn't end. Okay? This goes on forever. So in most situations, in most questions, the question will tell you the number of terms that you need to expand. Okay? And again, the higher the number of terms that you expand, the closer the overall result will be to the expansion that you have. Okay? So the new rules state that the N can take any value. Also, whatever X is must be comprehended between -1 and 1. And as I already mentioned, this series is infinite. It is not terminating. What if you have an expression? What if you find an expression in which A is not 1? Well, you can transform this into a situation like that. Okay? All you have to do is to factorize a. If you factorize a, then you open brackets, this obviously will be 1, and this will be x over a. And then you can extract this a to the power of n outside, and you have this, and if you compare this, is this situation. The difference is that instead of just having x, or whatever letter that you use as the unknown, you will have x over a, but the rule still applies. If you compare this to that, it's the same thing, but instead of x, you just have x over a. Okay? And the range of values for which this expansion is valid when you have x over a instead of just x is not going to be anymore between -1 and 1. You just have to do a very simple calculation. So whatever x over a is, if you would solve this equation, then it is the modulus of x that is smaller than a. In other words, this expansion would be valid between -a and a. Okay? All right, so this will be it for this lesson. You are going to understand by solving questions how this formula works. Again, looking at it, it seems too complicated, but it actually isn't. So practice with a few questions regarding the application of this formula, and then you'll be ready to tackle the second lesson that apparently doesn't have anything to do with this, but everything is going to be stitched together in our last lesson, in lesson 3.